And obviously I've told you before that we're going to be focusing initially on gradient, and that's the really critical part that you need to understand today. How to find the gradient at any point on a graph. And the graph doesn't have to be a straight line, because all we've ever done before is find the gradient of straight lines. But now we're going to find the gradient along curves. And that's what gets a little bit tricky. But if you actually break it down and go slowly and learn the process, it's not so bad. And what we're about to do today, you're going to find that we actually don't do in a couple of classes' time, because we've got a whole lot of little shortcuts and formulas that give us the answer almost instantly. Calculus is not that difficult. Differentiation is not that difficult. What causes people problems is the algebra behind it. So let's actually have a look at it. Now, dealing with calculus, we need to just turn this on. We're going to break it down into one of two parts. The first part we're going to deal with is what they call differentiation. Now, let's go back over what we've talked about before in the past. What's another word for gradient? Slope. Can you remember some of the other ones? Rise over run. What else?
y2 minus y1 over x2.
Good. y2 take y1 and x2 take x1. Anything else?
Tan theta.
Sorry? Tan theta. Yeah. What else? M? Yeah, we actually did that one. I haven't got that one listed. That was negative a on b, when you had the equation of a straight line in general form. That was how you found that. The gradient tells you how steep a line is. Here are 7 ways that we've talked about before. Okay? 7 different terms for gradient. Every single one of those we've pretty much mentioned. Today we're going to talk about an 8th way of describing gradient, which will lead on to a 9th, 10th, 11th and 12th and so on. There's a whole lot of ways that we can describe it. Now, just before we go on to looking at curved gradients, we've looked at this slide before. What happens if a gradient is 0? What do we know about a straight line if it has a gradient of 0?
It's horizontal.
Horizontal. What's the angle that it makes with the x-axis? 0 degrees. So it's a horizontal, it's got no steepness, it's flat. What if the gradient was 1?
45 degrees.
We know it's a 45 degree line because we know m equals tan theta, and if you do the inverse tan of 1 you get 45 degrees. What else do we know about a gradient of plus 1? It goes from left to right, uphill. So we say it's a positive gradient because it's going uphill from left to right. It's a positive number. What about a gradient of 5? When you compare it to a gradient of 1, bigger number, bigger gradient, steeper line. And the angle, we could find the angle. We know that 5 equals tan theta. If we did the inverse tan of 5, we'd get the angle, and it's around about 79 degrees if you plug it into your calculator. What about a gradient of minus 2.5? Left to right it goes downhill. Could you find the angle that it makes with the x-axis? Negative 2.5 equals tan theta. Do the inverse tan of minus 2.5, and you'll get roughly 68 degrees, but it's going downhill, remember. Now, let's take the 4 cases that we had with straight lines. Describe that gradient in words.
Positive.
Positive, what else?
Like gradient of 1.
In words, I don't want actually a numerical value, just a description. We know it's positive, what else? It is increasing. That's another way we describe it, when it's going uphill. Uphill, positive, increasing. What about the next one?
Negative and decreasing.
Negative and decreasing. What about the next one? How would we describe a horizontal line? It has no gradient at all. So it's got a 0 gradient. Is it increasing or decreasing? Neither. And the special word that we'll start to use is we'll say that it is stationary. It's got a 0 gradient, stationary, but we'll talk about that later. And the last one, and you don't tend to get a lot of these at the moment. What do we know about the gradient of a vertical line? Undefined. We don't have a numerical value for it. So there are 4 gradients that we come across when we're dealing with straight lines. Now let's up the level of difficulty in a second. On a graph, we can get what we call a rate of change. Now, what is a rate of change? A rate of change is how the dependent variable changes with respect to the independent variable. In other words, how y changes with respect to x, which is, what's y match up with? The rise. What's x match up with? The run. And if y is changing and x are changing, the rise and the run are changing, it's called a rate of change, and it's another way of describing gradient, which is another way of describing slope, or m, or rise over run. It's just another way of describing this concept of how steep something is, the rate of change, if we talk about it at a particular point in time. So another way that we're going to describe the gradient is the rate of change. Let's have a look at the first example in your booklets that you've got. We've got our diagram. Now when you look at your diagram, the question says the graph shows the average distance travelled by a person over time, find the gradient and describe it as a rate. This is a straight line question. We'll start with the easy ones. If I'm starting with a straight line, how can I find the gradient if I've got a picture? Rise over run. So here's my line. I might use this one here as my rise. What's my rise? How high does that climb?
800.
800. My run is the horizontal. How far does it go across? 10. So the rise over the run, 800 over 10. And you could draw that in if you wanted to. If you could see it and visualise it, you don't actually need to draw it on because it's a fairly obvious one. So when we look at this one here, we know the line's increasing. We know it's going to be positive because it's going uphill. We've discussed that. The rise over the run, we just said, was 800 over 10, which is 80. Now what does that actually mean? We need to actually find the gradient, which we've found, and now describe it as a rate.
80 metres a minute.
Well, what's this unit here? Meters. And this one is in minutes. We always use the vertical axis first. So we describe that by saying the person is travelling at the rate of 80 metres per minute. That's calculus. How much different is that from what you've just been doing? Not very different at all, except now we're giving it a name. So let's have a look at the second example. Another straight line graph, but the big difference with the second example is that the graph from left to right goes downhill. What does that mean? Negative graph. So if we look at the graph, the line's decreasing, it's going downhill, it's going to have a negative gradient. How do you find the gradient? Rise over run. Now I'm not going to actually draw this one on, but what would the rise be for this question? How high does it climb up? 500. How far does it run? 15. So if we do the rise over the run, it's going to be 500 over 15, but why have I put a minus sign in front of that?
Going downhill.
Because it's downhill, it's decreasing, it's negative gradient. If I divide them, that's a bit of a messy one. Works out to be minus 33 and a third if I write it as a mixed fraction. What does that mean? That's my gradient. The gradient's minus 33 and a third, but how would I describe it as a rate? What's the vertical axis? Accidents per year. So if I actually wanted to describe this as a rate, this is a little bit trickier because it's negative. I could say the rate is minus 33 and a third accidents per year, or if I didn't want to use the minus sign, I could say the number of accidents at the intersection are decreasing by 33 and a third accidents per year on average as we go along that line. So you're having just over 33 less accidents per year looking at the information there on that graph. So you don't have to put the minus sign if you use the word decreasing in front of it. But if you don't, then you need to put the minus sign there because the minus sign means it's a decreasing gradient. It's going downhill from left to right. So they're straight line situations. Finding the gradient of a straight line is fairly easy if you've got the information because you can use rise over run or you can use some of the other formulas that we've come across. They're called constant rates of change when we're dealing with straight lines. But I've told you we're not going to be dealing with straight lines all of the time. What are we going to be dealing with?
Curves.
Curves. Things all over the place. So the gradient or the steepness is going to be constantly changing. When you think of an example in real life, if you were driving a car, you're not going to be driving at the same speed the whole time. You're going to be accelerating and you're going to be braking and your speed will be all over the place. If you graph that, it's not going to be a straight line graph. There are plenty of graphs that you can draw that are real life graphs that are not straight line graphs. And we can use this concept of finding how steep our graph is at any point in time and use that to actually solve all sorts of questions. Let's have a look at this here. Now this is a messy little graph, but it's a super powerful graph. It's not in your booklets. So you just got to look at this and try and understand it. Now, for the moment, this is what we need to understand. The black graph, the curve, it's cubic. It's actually y equals x cubed minus 3x from memory when I put it into the computer. That's the cubic that I'm looking at. That's the one I'm focused on. Everything else, don't worry about it for the moment. If I look at that black graph, is it very steep here? Yeah, it's going uphill at a fairly steep rate. What happens as I get towards the top of this part here? The steepness, it just levels out. And what's the steepness rating, or what's the gradient at the turning point there?
0.
0. What's happening now to my gradient? Downhill, downhill, downhill. What's the gradient there?
0.
0 and uphill. Now what I want to do is I want to explain what the green line is. The green line is what we call a tangent. A tangent is at that particular dot, I draw my tangent in and it touches the curve only once. And that's actually representing how, if I can find the gradient of that tangent, the steepness of that green line, that's how steep my curve is at that dot, at that point. Don't worry about the red graph. We're going to refer to that in a few examples' time. That's actually something else altogether. So let's have a look now at this. Now, watch what happens as I move along the x-axis. My dot is moving, it's changing. What's happening to my green line consistently? The slope is changing. Notice what happened to the slope when I get to the top. The slope's 0. Over here I've got, they're the x and y values of that black point, and that's the gradient being given to you the whole time. Now, why am I going backwards and forwards here? The gradient is actually its largest negative value at 0, 0. What happens when I get down here? The gradient's 0 again. As I start to head off to the right, what should happen to the gradient? It's bigger and bigger and bigger. And look at the number getting bigger as it goes further up. So as you go through, you can see that green line. The angle is continually changing. The steepness is always being adjusted. And that is calculus. That's differentiation in a nutshell. You have to be able to, at any point, find how steep the curve is. So here's one option you've got. Draw the graph, draw in a tangent, use rise over run, find the gradient, and then we can find out how steep it is at that particular point in time. We don't want to do that because it's just a pain drawing the graph accurately, and it's very, very difficult to draw it accurately for some of the curves. And some of the curves that you actually get won't be as simple as a cubic, they'll be too hard to graph. We have a process called differentiation that we'll learn about later that will give us the value that allows us to find out how steep our curve is at any point in time. And as we're going to learn later on, the most important points, typically speaking, are where the gradient is equal to 0 because they give us a whole lot of information. So that's differentiation in a nutshell. Let's go to the next example. So it's the first example on the next section. Describe the gradient of the following curves. Is the steepness changing with this? It's not constant, is it? How would you describe the gradient to the left-hand side of the curve here? Increasing. How would you describe the gradient at the top? Stationary, or a gradient of 0. And how would you describe it to the right? Now this is what I'm going to do. I'm actually going to put some markers on. That's positive signs say it's a positive gradient, it's increasing. 0 gradient there, negative signs are just saying it's decreasing. So next to your graph, you can just put a couple of positive signs, negative signs, and it's a 0 at the top. So that's actually giving a little bit of a description that we can look at and recognise whether the gradient's positive or negative. Now it says to describe it. How would we describe it in words? We'd say Where the curve increases, the gradient's positive, and we can see that, that's where we put all the plus signs. Where the curve decreases, it's negative, that's where all my negative signs are. And where it turns around at the turning point, what's the gradient? 0. And that's often the most important point that we actually need to locate. And we can locate that without even drawing the graph, if we understand how to use calculus properly. But that's quite a few lessons away before we do that. At the moment, we're just focusing on what the concept is behind it. Let's have a go at the second example. You've got to put pluses and minuses in and describe where the graph's positive, where it's negative, where it's 0. So have a go at trying to fill that one in as quickly as you can. So just put a few pluses and minuses in the appropriate position, and then write what's happening when it's increasing, decreasing, and when it's 0 gradient.
What did you write for the 0 gradient, the description?
0 gradient?
Yeah, like when, in those words, where the curve...
Where the curve turns. Where the curve's at its turning point, the gradient is 0. So I'll put some pluses and minuses up on the board for you to check it with. So from left to right, the downhills are negative, the uphills are positive. You've got 2 turning points on this question, so you've got 2 positions of 0 gradient, but the description is identical to the last question. You can say wherever the graph is decreasing, it has a negative gradient. Wherever it's increasing, it has a positive gradient. And at a turning point, it has a 0 gradient. It's the same answer as the last question. But we can see from the graph where it's negative and where it's positive because I've put negative and positive signs in there. Once you've answered example 2, example 3 is the same concept. Put some plus and minus signs on example number 3, and it's going to be exactly the same answer. When it's going downhill from left to right, we've got a decreasing situation. When it's going uphill from left to right, we've got an increasing situation. At turning points, we've got a 0 gradient. So the answer is identical for examples 1, 2 and 3 for the writing part of it. The pluses and minuses are a bit different because the shapes of the graph are a bit different. So I put example 3 up now. You see I've got more than 2 turning points with this one. We've got pluses, we've got minuses, we've got 0 gradients floating around. But the word answer is identical, doesn't change. You think you get the concept there? Because we need to do that, use that concept to produce some gradient graphs in a moment. Gradient graphs, steepness graphs. We're going to actually produce a different graph from this one, and the graph that we produce is telling us how steep it is at any point in time. Right, over the page to example 4. This is a bit of a complex one. This is actually, if you look at the blue graph, that's the parabola y equals x squared. If you look at the red lines, I've put a couple of red lines in. This was an exercise, I don't know if I gave it to you guys in year 10, or I gave it to another group, but it was an exercise that I gave to a year 10 class, just to experiment with rise over run. If you look at this line here, that's actually the tangent at that point. It keeps on going, but I didn't extend it. What's that point there as a coordinate? It's the point -3, 9. Here I've got -3, 9. I want to know the gradient of the tangent at the point -3, 9. So if I could actually draw the gradient a little bit clearer, and there it is clearer, how do you find the gradient? How do I find the gradient of that red line? Just rise over run. Now where I actually draw my rise over my run doesn't matter. There's several spots I could choose, but I'm going to go for, that's my rise and that's my run, because that's with my red line. So there's my rise all the way down to the x-axis, because that's fairly easy. I know that's a distance of 9. What's that a distance of from there to there? You're going from -3 to -1.5, so how far have I travelled? 1.5. So I've got a rise of 9 and a run of 1.5. But what do I know about this line? From left to right it's going downhill, which means my gradient's minus 9 over 1.5, which cancels to minus 6. So I come up here, what do I put the gradient at that point is? Minus 6. So I can fill the table in. That's a whole lot of work just for one gradient. Let's go to the next point, negative 2 comma 4. That's that point there, out 2, up 4. At negative 2 comma 4, I can see my tangent. I've just made it a little bit darker so you can see it. I've got to find the rise over the run. There's my rise, there's my run. Oh, where's my run? There it is. Rise, how far has it risen? 4? What's the run? 1. So the rise over the run is 4 over 1, but it's downhill, so it's minus 4 over 1. So my gradient at that point is minus 4. It actually has a different steepness level. Which one's steeper, minus 6 or minus 4? Well, minus 6 is a much steeper downhill drop than a minus 4. What's going to happen when I get to minus 1, minus 1 comma 1, that point there? Does it look like it's steeper, or does it look like it's less steep at that point? Less steep. Now I haven't got any more tangents drawn in or rises over runs. Let's just think about this one now. I can see my little red line going through there. What would the rise over the run be for that one? How far has it risen?
1 over
1 over a half. What's 1 over a half? 2. And it's downhill, so I'll end up with minus 2 in there. What's the gradient at 0, 0? 0, because it's going to be flat. If I go to 1, 1, see how it's a mirror image of that point there? When you actually calculate the gradient, it's going to be exactly the same steepness rating, except instead of going downhill, it's going uphill, which means instead of having a gradient of minus 2, I'll end up with a gradient of plus 2. What do you think the gradient of that one would be? Plus 4, and this one here? Plus 6, because they'll mirror each other, because it's a symmetrical graph. So there's our values for our gradients. Now I'm going to draw a gradient graph. And that's what you've got underneath. Notice it's no longer called a y-axis. What's it called? The gradient axis. So, when x is minus 3, what's the gradient? Minus 6. So you go out to minus 3, down to minus 6, and you put a dot. When x is minus 2, I don't want to know what y is, I want to know what the gradient is. This is a gradient graph. It's not a y versus x graph, it's a gradient versus x graph. And so you put all of those points on, and they should end up, in this case, looking something like that. And I could join them together, and that's my gradient graph. So I'm looking at the x value and the gradient value, the x value, the gradient value. Put all the points together and there's a gradient graph. Gradient graph is very different to the original graph, but this graph here will tell me how steep I am at any point in time. If I want to go to the original blue graph and I want it to go to a half, that's not one of the dots I've got here. If I go to a half, how steep is it there? I could come over here, could go out to a half, go up to there. Looks to me like it's got a steepness rating of 1. So I know that at there, it's got a gradient of 1. The gradient is continually changing. How can I figure out the gradient at any point on the graph? Look over here. And I'll just read it off. The y value is not a y value, it's the gradient of the graph. That's differentiation. And that is what holds people back. And if you understand what we're doing, you're halfway there now. You've just got to get the algebra part sorted out. Let's go to the next one. We're actually going to draw this now without using tangents or anything like that. It's just going to be a bit of rough sketch work. So here's my first graph. Sketch the gradient function for the following graph. Now, this is where I'm going to put the gradient function. Now, what do we remember about these graphs? Well, I could actually go and put my pluses and minuses in, but I want to go back. Remember when I looked earlier on at this green line as it was moving around? I said, let's ignore the red parabola. Must have got an email. Let's ignore the red parabola. I'm going to look at it now. That red parabola in this case, is the gradient graph. Just like that last example, you drew a gradient graph that was a straight line. For this question, for my cubic, the black line or the black curve there, the gradient graph is a parabola. That's the gradient value. Now, if I look at this spot here, and that was at minus 1, 2 on this graph, if I look at that, go left 1 up to, what's the gradient? 0, isn't it? So when I look at my gradient graph, where will it actually cut the x-axis? If the gradient's 0, it doesn't go up, it doesn't go down, it cuts it on the axis there. Let's try and transfer that across here. Where will my gradient be 0? At a turning point. How many turning points do I have here? 3. So that means I'm going to have 3 positions where the gradient will equal 0. Now, above the x-axis means the gradient's positive. Below the x-axis means the gradient's negative. On the x-axis means the gradient is 0. So I've now got negatives and positives like I put on my earlier graphs. If I focus on the 3 turning points, let's put some vertical lines through those turning points. That's the low point, the high point, the low point. I come down to my new gradient graph. What's the gradient there? 0. What's the gradient there? 0. What's the gradient there? 0. So if I wanted to, I could come down here and I could say, on my new graph, I know it's going to touch the x-axis at those 3 spots, those 3 positions. Now, is the gradient positive or negative to the left of x1?
Negative.
Negative. Does that mean it'll be below or above? Below. Always positive, which means it will be above. Negative means below. Positive means above. And when I start to draw my graph in, let's see if this matches up. Is the graph to the left of this dotted line? It should be negative. It should always be underneath the x-axis. Yes. The graph here, all the way out to x2, should always be above the x-axis, which it is. But you'll notice there's a high point there. How do I know where to put that? I don't. I don't have enough information yet. So I don't worry about that. I'll just guess.
Isn't it going down before the...
Well, what's actually happening is it starts off at a 0 gradient and it gets steeper and steeper and steeper and steeper and steeper and steeper and steeper until it hits that spot there, and then it starts to flatten off again. That's the steep. So it's getting steeper and steeper and steeper and steeper and steeper, reaches its maximum steepness, and now it's starting to ease off again until it gets flat. So it's getting steeper and steeper and steeper and steeper and steeper. It reaches its maximum steepness, then it starts to flatten off again. That's what's happening. These are always negative, so they're always underneath. And again, it's getting steeper and steeper and steeper on a downhill run, steeper and steeper. When it gets to there, what's happening? It's getting less and less steep because it's starting to head towards flattening out again. And that's why it goes to a low point and then it comes back up. To the right, it's always positive. Now that is a Year 12 class. And we've just been doing this only about a week ago. That's one of the harder aspects of differentiation. And hopefully you're sort of thinking, well, it's not too bad. Yeah, it's a little bit tricky, but it's not too bad. If you're getting the concept here, you're actually grasping some of the hardest parts of differentiation. Let's look at our last example. Where, and this is a little bit misleading to see if I can trick you, where am I interested in transferring 0 gradients? At x1, x2 and x3? No, because where do 0 gradients occur? At the maximum and at the minimum, at the 2 turning points. So if I actually went and put my plus and minuses in so I could see where it's going to be positive, where it's going to be negative, I looked at my vertical lines that drop down, that's where there's a turning point, that's where there's a turning point. To the left of my first 0 value, will my gradient graph be above the x-axis or below the x-axis? What does a plus mean? Above or below? Above, because the gradient value has to be a positive value. So it's going to be above. What's it going to be between these 2 dotted lines? Below. What's it going to be to the right of the dotted lines? Above. And if we draw it in, it looks something like that. You'll start to learn a cubic will go to a parabola. A parabola will go to a line. 2 turning points goes to 1 turning point. 3 turning points goes to 2 turning. You always lose a turning point when you actually differentiate these sorts of curves. There you have it. Time to do some questions. Thank you.